Okay, so we are speaking about exponential functions today, and as you can see by those graphs, they grow at a very, very, very fast, or they decrease at a very, very, very fast rate. When we look at these graphs, we're going to always start from the left and go to the right. So when I look at these are all growing. So it's starting off small, and then it's increasing upward, okay? Does that make sense? Starting from the left, going to the right, we're starting off low and then increasing. If we were going to be decreasing or having a decay, then the line would do the exact opposite. It would basically be starting up high and then dropping down low. Okay? The formula that we see there that I talked about is going to be y equals a times b to the x power. So if I wanted to write that in, over here we've got y equals a times b to the x power. So the a is the first number, the b is the second number. Show them, we still have the domain and range, that's still there, it's not changing, that's still super important. Domain is still referring to all of our x values. Well, let's talk about this for just a second. These graphs still have arrows on here. And so if I have the arrows on the end of my graph, what does that mean about my domain? What is it going to be, Tommy? It's going to go forever and ever and ever. And so just like with quadratics, our domain is still going to be all real numbers. The domain is going to be all real numbers. Pretty easy, right? Good. Now my range, however, and this is where we're going to get more into detail here shortly. Notice that as I'm drawing this line here, it's getting closer and closer to the x value. But notice that it's just continuing to go on and on and on and on and on. That line is never going to break below the x-axis. Here's why. If we're talking about growth within a number, and we're talking about it growing exponentially, the only way that it can ever equal 0 or become negative would mean it has to be multiplied by something that's 0 or negative. This exponential equation, which we're going to talk about in just a second, does involve time. And so with the time, you can't have a negative amount of time. If you have a negative amount of time, what that ends up doing is dropping down below. So we can get really, really close, like down to the day, the minute, the hour, the second, the millisecond, but we can never break that threshold. So that means that your range is going to have to be all real numbers greater than 0. You're okay with that? So y is all real numbers greater than or equal to 0. All right, now we got this really funny word. It's called an asymptote.
Okay.
Asymptote. And an asymptote, let's see if I can find the technical definition, is a line that a graph of a function gets closer to as x or y gets larger in absolute value. So your asymptote is how we actually describe this right here. This piece, how it's getting closer and closer to that value. It's never going to actually touch it, but it's going to get closer and closer and closer and smaller and smaller and smaller. So for this particular problem, we would call the asymptote 0. Because this x value, or this y value, I'm sorry, is getting closer to 0 without ever actually touching it. Okay, so let me recap what I've done so far. Domain, still all of our x values. Range is still all of our y values. And asymptote is where that line starts getting really, really, really close to that line. Okay. X-intercept has not changed at all. Is there going to be an x-intercept on this line if we never cross the x-axis? No. So the correct answer for x-intercept is none. How about a y-intercept? Does anybody see the y-intercept? It's 1. Okay, what I'd like you to do is go ahead and open up your calculators, please, for today on your computer. Go ahead, open up your calculator. And when you get to your calculator, I'd like you to go to your y equals, and I want you to type in this equation right here. Now, yeah, you're going to have to make your exponent a variable. That's okay. So literally, you're going to type in y equals 1 divided by 2 times 3. Then you're going to use that little caret top. Then you're going to put the x as your exponent. And then hit graph. So again, nothing's changing. We're still able to graph all of these pieces out. We're still able to get them onto our calculator if you're just given the equation and graph it from there. Okay, now let's talk about what the a, b, and the x stand for. Okay, so this is the piece that I want you to add to that notes or to your journal, whichever you prefer. A is our initial value. That's what we're starting off with. A is our initial value. That's what we're starting off with. B is our multiplier. Now when I say multiplier, I'm sure you guys have all at least played a video game or an arcade game where you get like a ×2 or a ×3 bonus on something. Yeah. That's what I'm referring to. We're just multiplying that number by this many multipliers. That's all it is. Doubling your score, tripling your score, whatever the case may be. And then finally your exponent is going to be your time. Your x or your exponent is going to be your time. Okay, so let's break down this first one with that information. Let's say you have 50 cents. I'm just going to take a money value because that's just how my brain works sometimes. And you get to multiply it by 3. That's your interest rate, or that's how much you're accruing over this amount of time. It's over X amount of time, which is a value that we don't know. We want to see what's the payoff going to be, and that's why our exponent or our variable is in the number or the time value. Okay. So where have I lost you so far? Where have I confused you? We're okay. Okay, I'm going to erase this part and move on to the second piece. All right, number 2. Domain, once again, is going to be what? All real numbers. Every time, y'all. Every time. Range looks pretty similar to what the last one looked like. So I would say it's going to be y is greater than or equal to 0. My asymptote, once again, is going to be what? 0. Now, it's not always the case, but for the majority of them, that will be what it comes out to be. And I'll make sure I show you some examples where it's not, but for the most part, this is what it's going to be. And then finally, do we have an x-intercept? No. Nope. Do we have a y-intercept? Yes. 1. Okay, now, go to your graph again in your calculator. I'm going to show you how to type in this particular one. So we're going to have y equals 4. Then you're going to hit that caret top. And when you hit that caret top, you're literally just going to type in x minus 3. Don't hit any of the arrows because it's going to keep the x minus 3 up tiny.
And then hit graph.
And then hit graph. Does it come out looking pretty similar?
It goes a lot farther now.
Yeah.
It goes farther, what do you mean? Goes further out? Okay, okay. Did you put a -3 or -3? Now, let me explain to you what this is trying to accomplish. I don't know why, maybe it's, we'll have to look at it more specifically, but it is supposed to produce the same one. What it means with that x minus 3 is if x is our time, there might be a 3-year penalty. Or there might be an amount of time that you have to wait to accrue that. You might have to wait to get to a certain point before you can actually start making money off of it. So that's why you have that -3 there. But again, we're still following that same basic principle. A is my starting point. B is my multiplier. So guess what? We just don't have a multiplier in this. The multiplier would just be 1. You don't need to write 1 if it's not changing anything. Okay, moving right along. Okay, as you can see for these ones, the graphs look pretty much the same. We're basically on the exact same thing with number 3. Number 4 changes ever so slightly. It's just showing that it comes back a little bit wider, or not as gradually quick, but they're all improving or increasing, which means they're all showing growth. Okay, now, it says without actually graphing, describe how the graphs of the following functions are related to y equals 5 to the x power. I don't care if you graph it. I think if you're given those resources, we should use it. One thing I want to make you very clear about, though, is that when you have a negative, it's going to change everything. So let's go ahead and graph y equals 5 to the x power. Go ahead and graph y equals 5 to the x power. AJ, how am I doing on time on the recording?
10 minutes, almost 11.
Okay, now as you can see, that one looks very similar to the ones that we've just seen. When you flip it, though, and you make it y equals negative 5 to the x power, what do you think is going to happen? It's going to make your graph go down. So go ahead and graph that one. You can even put it in the y2 if you want to compare them. And it literally should be the exact same thing but going down. Let's talk about that, though. If you multiply a positive number by a negative number, doesn't it make the entire graph become negative? Yeah. So we shouldn't be confused by that. It's not changing anything. And that problem is going to amount to all of this. Anytime that you have a negative value, it's going to make this have a decay or a negative graph. So let me ask you this. Is this going to have a growth or a decay? Growth or decay? Growth or decay? Okay, that's all there is to it. What I want you to do now is, you've already got this as your base one that you're looking at. I want you to go ahead and graph these next 3 and just kind of get an idea of what they look like in comparison to that one. So you're just graphing them. You're just looking at them and comparing them, essentially like we did with the parent function. You're just seeing how they look, how they change, what differs between them and the originals.